given you zinc and HCl. He's given you NaBH4. ये थोड़ा सा problem है. This part I can sense there is something wrong here. This 9th May, there is something wrong here. I do not remember what is wrong here exactly. I will have to think about it and get back to you. My gut feeling tells me it goes like this. LiLH4 can do it for, I think, 1 degree. And NaBH4 can do it for secondary and tertiary, I think. Something is wrong here.
Okay.
I will get back to you on this here. Something seems to be wrong over here. I'll get back to you on this. I'll have to check up some data here. I'll have to do some research for myself as well. My brain is not giving me the correct answer here, but it's telling me there is something issue here. So this part here, don't think too much over here for this. There seems to be something funny here. Next is reduction with HI red phosphorus. Yeah, this is true. This will happen for everything. HI red phosphorus is like destruction. It will destroy anything and everything. And any problems with the HI red phosphorus thing there?
No.
Okay, all right. Now, from Grignard reagent, what did you have in terms of understanding there?
So we're given like 4 lines on it.
So what you can try to link this Grignard reagent thingy up with is the fact that this is going to be something which is going to be one of the easiest methods.
Yeah, there is a chapter, just
yes,
a chapter called Grignard reagent.
Completely separately. There is no problem at all about that. But the key thing which you need to understand here is this reaction is going to be easily happening. RMGX plus any acid. Water doesn't have to be here. It can be any acid. Water is a very, very weak acid, correct?
Yes, very weak.
Even that guy can do this. So any acid, any substance which you can dream of reacting as an acid will give you the alkene here with this. That is because the RMGX. What is it RMGX similar to?
Anion.
Correct. It is similar to a carb anion. So you can definitely think of it as being similar to a carb anion for sure. Okay.
Wait. Should be a carbocation. Wait.
Think. Who is the fellow who is attached to my carbon there?
A metal and then a halogen.
Halogen. What is the charge that we can take?
Minus.
Minus what?
-1.
-1.
Oh, I see. Okay. Yeah. Good.
What will that metal take?
+1. +2. +2. My bad.
It will prefer a +2, right?
R will be -1.
So that's the idea.
So with this information, I don't think I can do those questions, right?
You are not supposed to be able to.
Okay.
So when you say questions, what are you saying exactly?
Like there was a chapter called Grignard's reagent in MS Java.
Yeah, you can't touch.
Okay.
Not right now.
Yeah.
Now, next is Clemmensen's reduction. You had your dinner in the meantime, yes?
Some of it, yeah.
Your bowl came, right?
Yeah.
Oh, cool. I just want to confirm that because I didn't want to make you starve and also sleep deprived. That is not fair. You're okay with pushing the class a little bit longer, I suppose, yes? Or you want me to shut up?
A little longer, it's fine. Yeah.
Cool. Now let's continue. So Clemmensen's reduction. So Grignard, I'm assuming you have cleared off with this over here. It's similar to a carb anion.
Yes. Yeah.
Yes?
Yes, sir. Yeah.
Clemmensen's reduction. Now, what do you need to know about in Clemmensen's reduction? Clemmensen's reduction, no need of all of this stuff. You don't need this much information on Clemmensen's reduction. Beta elimination. This is alkenes. Okay, reactions is okay. Clemmensen.
Isn't the first page I sent you?
Yeah, I know.
Yeah.
So this was your Clemmensen's part there. So Clemmensen's, your teacher has given you a little bit extra information here, which is not really required as of now. all you need to understand is aldehyde or ketone. Okay, can be reduced or converted into alkane directly. So how should you put down the synopsis for the Clemmensens here? Whatever your sir has given is acceptable amount in terms of synopsis to an extent. But the problem is you don't need the mechanism. Mechanisms ko nikal do, it is relatively acceptable whatever you have put there. Did you understand what you put down there though?
Not completely. No.
Can you address the points? If you point out the points, I will give you answers for what.
Like the mechanism, I didn't really understand what's happening.
I'm not going to touch the mechanism. I told you it's not needed. Other than
But
the
other
mechanism.
than that, yeah, then it's fine.
Oh, really? You understood what acid sensitive groups mean?
I don't know what that is. That I didn't understand.
That's what I was asking, na?
Sorry, I didn't see that point. Yeah, I didn't understand that.
So the idea here is your teacher gave you the mechanism to compensate for that. See, whenever a teacher is basically giving you extra information which is not required at that stage, why would they give it to you? Because they have something to explain which is requiring that extra bit of detail. In this case here, to explain this acid sensitive nonsense, he basically had to do it. So the idea here is when you are having Wolff-Kishner reduction being done, it is something which is done at concentrated acidic condition. So any medium which can react with that acidic medium will not be something which is going to be doing the reaction in the expected manner. It will give unexpected products. So alkenes, alkynes, and alcohols react with acids. Why? Because they are generally electron-rich species. Alkene has a pi bond. Yes or no?
Yes, sir. Yeah, makes sense.
Alkyne also has a pi bond.
2.
So both of them are electron-rich species. Pi clouds are electron-rich.
Yeah.
Similarly, alcohol has an OH group attached to a carbon. That means think of water. Water, if I replace a hydrogen with an alkyl group, the alkyl is a plus I group.
Yes.
That means the oxygen now in the alcohol is more donating.
More negative.
More
Yes.
donating in terms of character compared to water.
Yes.
So it's more electron rich.
Oh, yeah. Yes.
So that's the idea there. Now, Wolff-Kishner reduction, on the other hand, is the same reaction or the same net reaction, but it is done in completely strong basic medium.
Basic KOH.
So in this particular case here, you should avoid anything which can react with the basic medium.
Exact opposite.
These groups as base sensitive groups.
I see. Okay.
So we avoid base sensitive groups in this particular case here. That is what they have mentioned here. Base sensitive, now it should not react with the basic medium. Look at the compounds here. What have they given? Have a look. Carboxylic acid. It will react with the basic medium. Sulfonic acid.
Yes.
Reacts with the basic medium. These are all again groups which will form salt with the basic medium. So halogen again can react with the basic medium. So you need to avoid something which can react with the basic medium. That's the basic purpose here. So when you're going to be having this particular, Wolff-Kishner reduction, this and the Clemmensen reduction are basically going to be doing only one thing for you. Converting the aldehyde or ketone into the alkane.
Alcohol. Alkene. Okay.
Alkane, not alkene. Alkane.
Yes.
But the aldehyde or ketone becomes the alkane in both cases comfortably, but in Wolff-Kishner, it does it in concentrated acidic medium. In the, in the Clemmensens, it does it in
basic medium.
And in Wolff-Kishner, it does it in concentrated basic medium. Means you need to understand that both are meant for different types of compounds with different extra groups present.
Yes.
That's the idea. Yeah. Now, let's continue. Don't give a crap about the mechanism in both cases. Mozingo is again bullshit. Okay? Mozingo is bullshit. You will never get Mozingo. Mozingo is not part of JE. Mozingo is bullshit, which you will see in MS Chauhan. So to make sure that the kids can solve it, sir has given you Mozingo there. That's why Mozingo is like a very clean synopsis already. No confusion in Mozingo, na?
No, sir.
Figured. Carbides are going to be things which you learn more about in later topics. Don't worry about them so much right now. Those are not really critical right now. Hydrogen transfer method, that is just bullshit. Don't care about that. So last two, in fact, last three, प्रणाम करके निकल जाओ. Mozingo to रखो थोड़ा सा, it might be useful in some nonsense. Carbides will be useful for later topics. The hydrogen transfer is just. Thank you.
Yeah.
Now, next, let's go for your other parts of the synapses, the properties of alkanes. So, you've talked about branching, melting point. Okay. There is one point which, okay, you've added that. Nice. But you've not explained it. So, this
Density.
is the. Yes.
The density thing.
Huh?
Which part, sir?
This part.
Oh, yeah, I didn't understand that. No. Yeah.
So, the idea there is melting point level, you're going to be having the temperature melting point is actually going to be a transition temperature between a solid and a liquid. Okay. Yeah.
Solid liquid. Yes. Yeah.
So when you're looking at a solid there, the more efficiently the solid can be packed. The particles of the pieces or the pieces present, if they can be packed in more efficiently, then you're going to be having melting point being more higher. It can remain as a solid for longer, basically. If it is not capable of being packed in properly, melting point will be lower. Now think of a packing here. If the molecule is going to be in a proper shape, which is going to be occupying lesser space, it will get packed better. So what kind of molecules do you think will be ideally undergoing a better form of packing? Molecules are spherical.
Spherical, yes. Yeah.
Right.
Yeah.
Ideally, think if I'm giving you a box, a big
Less
card,
surface area.
if I'm giving you random objects to pack, what do you ideally want that object to be if you have to pack it as nicely as possible? You like boxes, same shape, effectively you like something which is going to be like
yeah,
which can be packed efficiently.
Yes.
But that's because of the shape of the box there, right? If the box was spherical in shape,
yeah, then you don't space.
Ideally, the scenario here is if you don't have a well-defined space, you'd prefer a sphere. The more spherical the object is, the better it can be packed. So that is effectively what's happening over here also. Melting point level, the packing will start mattering a little bit more than the boiling point. In boiling point, what matters is the lesser the branching, the better you're going to be having the boiling point. Why? Because if there is lesser branching, that means the molecule is occupying more space. Right? If it occupies more space, then there is a greater chance for it to interact with its neighbors.
Yeah.
See, if you are lying down on your bench in a very Shavasana type of scenario, more kids around you can poke you or interact with you in some way, correct?
Yeah.
If you're going to be curling up in a ball, well, you protect all your organs and you don't get beaten up properly. Why is that working out? Because you're offering lesser space for contact.
Yeah. Surface area should be minimum.
Surface area is going to be lesser. The exposed area. So that is basically the idea over here. So boiling point is going to be something which will depend on something different than the melting point normally. Slightly different at least. All right. Melting point is going to be something which depends more on the molecule's shape being spherical in nature. The more spherical it is, the better sometimes it is going to be. But this branching part is applicable over there also when you're comparing similar species. If you're comparing completely, large molecules, one which is going to be having more spherical shape, then it will work out in the reverse that this part alone does not seem correct here. This.
Hmm.
This and this are correct. This is not perfectly correct. This is fully
For
correct.
isomers.
Yeah, even for isomers. One by branching is not the case there. The more spherical the molecule is going to be eventually, the greater the melting point is going to be. The more closer to a sphere. So if I have something which is a neopentane type of thing,
Hmm.
that will
It's like
have
a sphere. Huh.
yes, exactly.
Hmm.
That flow will be having slightly higher compared to its other isomers, which are long chain, melting point wise at least, expected to.
Okay, understood. Yeah. Oh, okay.
என்னடா ஓ வந்தது? No, seriously. Okay, now let's get to the next thing here. Density of alkanes. Again, nonsense. No requirement to bother with density of alkanes. They're all very tiny. Densities are very tiny. Chemical properties, free radical substitution. This part, you've got whatever you need over here. Plus, 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 plus only. But we have talked about this already. In this here, the energy profile diagram part here. Why do I not need to give a shit about this?
It's implied already. I mean,
everything is implied there. You don't need the energy profile diagram. This reaction depends on the goddamn catalyst.
Yeah.
Catalyst is the one which will break the bond which needs to be broken.
Yeah.
Which is my first step. Correct?
Yes, sir.
So the catalyst takes care of the pain in the entire process here. So the remaining things automatically just fall into place. Now, the key things which you need to pay attention to here in this reaction are not exactly this alone. Some other sideways nonsenses here, as you have mentioned here. Pay attention to what I'm pointing here. What am I pointing to here? I'm pointing to the R there, correct?
Dimerization.
Yes. So in some of these questions here, in free radical reactions, one of the key things which you need to pay attention to is there will be trace products obtained.
Yes, minor products, yeah.
Don't call them minor, they are trace. Minor means they are obtained in reasonable quantity. Wording matters.
Okay.
All right. If I'm going to be having, say, a product obtained as a major product, that means it is obtained at least, like, say, 20-30% yield. All right. Minor product, now at least 5 or 10% of it is obtained. Base product, now it is obtained in tiny fractions. Like, say, a few molecules out of a few billions. Which will still work out like, say, 0.001% or 0.01% or some shit like that. Those are called trace products. This guy is not a minor product. This guy is a trace product. Am I clear with that? So
why
you
is it
can
like that?
Trace products. What are the other trace products possible here? You can
Why is it like that?
You're doing methane plus chlorine, correct?
Yeah.
But you can get ethyl chloride as a minor product. I mean, not minor, as a trace product. Why?
But then why is it trace? Why is it not minor?
Think.
Or major?
This RR has to be producing ethane first.
Yes. Oh, okay.
And then that guy should do halogenation, correct?
It could happen, but is it okay? It's like
it is not about it could happen. I'm not debating whether it could happen or not. I agree it could
very
happen.
less chance. Yes.
I'm looking at the probability of it happening.
Understand. Yes. Understand.
You understand the idea here? You are only
Yes,
still stressing upon the possibility. Possibility is just the first stage of understanding. The possibility should be converted into a probability eventually.
Okay, understood. Yes.
So you're going to be having those possibilities as trace products over there. Okay, let's move on to the next page now. I would like to at least complete alkanes today.
Yeah.
From the synopsis. Alkenes, when are you planning on writing this?
So I wrote a little bit already, but then it's not too much.
Some parts of reactions, then you went into alkenes directly.
Yeah.
Anyway, reaction with I2. You have mentioned iodination is carried out in the presence of an oxidizing agent.
You gave that point. Yeah.
But you mentioned it also here. You mentioned it means your teacher has already discussed that. But
Yeah, he
what
did. Yeah.
you just never connected the pieces properly.
Yeah. I agree. Yes.
So we have already discussed all of this to an extent now. I suppose you understand how to basically write this better now. None of
Yes, sir.
this crap here,
Yeah.
please.
Mhm.
All right, none of this crap here. Make sure you are making this as efficient as possible in terms of the way you put it down. Nitration. Anything meaningful to discuss there? Absolutely not.
Yeah.
Why? Because it's a
Sulfonation.
reaction. Okay, what is HONO2? Corn nitric acid. Nitric acid is a goddamn extremely powerful oxidizing agent. So, no, this is going to be something which will happen, yes, but you don't need to care about it so much. Same goes for sulfonation. Pyrolysis or cracking is again a bullshit reaction. Isomerization is also a bullshit reaction. These are reactions. Among these here, nitration and sulfonation are complete bullshit reactions from JE point of view also. But
Okay.
pyrolysis, cracking, and isomerization and aromatization, these three are necessary
Later
reactions because
parts.
they are in NCRT.
Okay.
So these three are given in NCRT, so you need to know them. Now, pyrolysis, you don't need to know much. All you need to know is it breaks the shit down. Extreme heat, nothing else to react with, it breaks down. Nothing else.
Okay.
You have a question on pyrolysis? Ask it off.
No, nothing. I mean, there's nothing to ask also. Yeah.
Exactly. There's nothing much to ask. You just heat it in extreme conditions. It breaks down into its pieces, however it can. Next, isomerization is something which is going to be going via a particular mechanism.
Sir, wait, I have a doubt actually in pyrolysis.
Yes.
Could ethine be found?
One second. Which one are you asking on?
The pyrolysis one.
Pyrolysis.
Kind of,
Okay.
yes. Could ethine be found?
Ethine. Possible. Possible. Possible.
Okay.
Because the ethene fellow, on heating strongly, can break into ethine and hydrogen gas. Possible.
Okay, fine.
Possible. Can happen.
Yeah.
Now, should you bother about it so much?
No.
Correct. Correct. That is the other point which I wanted to make sure you understood as well. You don't need to give a shit about whether you really get ethine here. Because pyrolysis as a question is never going to ever get asked. Why? Because it is something which is like a flat fact-based reaction, which is useful from a JEE main standpoint, provided they are asking the exact same details in the NCERT textbook, which I'm sure you will definitely swallow by the end. Now, coming to isomerization. The key point to remember in isomerization is usually in this isomerization reaction, you use a strong Lewis acid. AlCl3 is what is called as a Lewis acid. Okay, you are familiar with what a Lewis acid is? Yes?
Yes, sir. Yeah.
So, this AlCl3 is a very strong Lewis acid, and we specifically use that guy over here. What can that tell you here? What does it tell you? When there is an acid.
This acts as a base.
This is an acid. Correct?
So this carbon thing is a base.
Good. What will happen to the carbon thing then usually? What do you think might happen? If it's a base, logically I told you, what is the name I called this? AlCl3. I called it what type of acid?
Lewis acid.
Good. What does Lewis acid do?
Second. Donates electron pair.
Reverse.
Oh, sorry. It takes, my bad. No, yeah.
It accepts electrons. Whereas the Lewis base or whatever is going to be behaving in some way or another as a base will end up forcibly giving electrons. Correct? So if this bugger, the compound over here, somehow or the other gives some electrons.
So, but what electron transfer is happening here?
Don't think about what happens. Stop thinking too much. Stop thinking about the product. Think about the nature. So if this fellow gives electrons in some way or another, The final product formed should be or the middle filler formed will be something which is not having enough electrons.
Carbanion.
Could be a
Carbocation.
possible mechanism flow here,
Free radical.
or
Ionic.
Ionic.
Carbocation.
Is there any ionic? Stop calling shit ionic.
Carbocation.
Carbocation. I do not want to hear this shitty word ionic ever again. All right, that's a very shitty generic word which just messes up the things over there. No ionic. I don't want to hear ionic anymore. Your teacher might give it. Don't follow ionic. Call it what it has to be. Is it a carbocation? Is it a carbon free radical? Is it a carbanion? Is it an organometallic? These are your 4 things.
Okay.
The carbanion and organometallic, your teacher seems to like to use ionic there.
Yeah.
So in this case here, it is not ionic for sure in that sense, but it is going to be carbocation predominantly. All right,
yes.
that is why you are able to get these weird isomeric properties over there.
Oh, hydrogen shift, methyl shift, how that happens.
Oh, you have done shifting of carbocations?
Yes.
That's why. Exactly. That's what's happening.
Okay, that makes sense.
All right, so you get a carbocation in the interim there that will do rearrangements, and that rearrangement results in your isomerization actually happening.
Okay.
Now, next, heat of combustion.